All right, let's get into something else. We were doing logs last time. We'll do rate of change. It's a pretty easy topic, not a whole lot going on here. There are two types of rates of change. Rates of change is just a fancy word for slope. So it's called rate of change or rates of change. All this means is the slope, the m value, mx plus b. It's this, the m. There are two types. One of them is called the average rate of change, average. And I'm gonna abbreviate this with AROC, average rate of change. It's pretty simple for a linear function. Let's say you have this function here. It's just a straight line, 3x plus 9. The slope is 3, right? Is it 3 everywhere? Like if you compare this to this, what's the slope here? It's going to be a 3, right?
Mm-hmm.
What about down here? What's the slope down here?
3.
3, right? So it's going to be 3 everywhere for a straight line. If you have the m value, you have everything. But things get a little bit more complicated when you don't have a straight line. Let's say you have a quadratic or something like that. Now for this function, is the slope here going to be the same as the slope over here?
No.
No, right? It's going to be changing. If you have a curve, if you have any other function apart from a linear, then the slope is going to be constantly changing. It's not going to be 3 or something. So how do you find the slope of a curve? The first way is called the average rate of change. You take 2 points, two x values, a and b. A is the smaller x value, b is the larger x value. So here we can go from maybe -1 on the x to, let's go, I don't know, like 5 on the x. So here, this would be your a value. This would be your b value. What you do is you take this point and you take that point, whatever the y values there may be, and you connect them like this. This line that we just drew from -1 to +5, this is called the secant line, S-E-C-A-N-T line. If you remember, secant is the reciprocal of which trig function, sine, cosine, or cotangent. Or sine, cosine, or tan. These are the primary trig functions, right? If you flip them, you would get, what's 1 over sine? It is cosecant, CSC. What's 1 over cos? It's SEC, secant. These are called the secondary trig functions, not primary, secondary. If you flip the primary ones upside down, you get the secondary. For tan, it's 1 over tan, it's the cotangent. This is not a trig unit, but the secant is the same as the secant over here.
Mm-hmm.
So that's the average rate of change. You need two x values, you draw a straight line, and this will always be linear. And then you find the slope of this line by doing rise over run or whatever method you prefer. If you want the formula approach, the formula for a slope of a secant line is this. So AROC, the average rate of change, is the slope of the secant line. That is going to be f of b, the y value when the x value is b, minus f of a, the y value when the x value is a, all over b minus a. So this is the average rate of change. Sometimes they will give you a table of values. Sometimes they will give you a curve. It doesn't matter. The formula is going to be exactly the same. So over here, we don't really need anything else. We're given a table of values. Looks like the function is increasing, and the question is asking us, during which 2-hour interval did the bacteria population grow the fastest? Now they're asking for an interval. Interval is an average rate of change. If they ask you for the rate of change over an interval. So the way to do this is you take your two y values, you take your two x values, and you use the formula. So during the first 2 hours from 0 to 2, what's the y value when x is 2? From the table of values.
1,122.
So it's 1122. So that's your b. 2 is your b. Now a is your 0. And minus f of a would be 850 all over 2 minus 0. So let's plug this in. 1122 minus 850 divided by 2. The answer is 136. So that's your rate of change between the hours of 0 to 2. What's the unit of rate of change? So you have some function going up like this, it appears. It's definitely not a straight line, could be a quadratic, could be an exponential. On the y-axis, we have the number of bacteria. On the x-axis, we have time in hours. Now the question is, what's the unit of the slope here? You take between 0 to 2. So what we just did right now is we found the slope of the secant line when the x value was 2 and when the x value was between 0 and 2. Now, if you turn this into a triangle, this is your rise, this is your run. The formula for slope is rise over run. Similarly, the units for slope is also rise over run. What's the unit over here? What's the unit of the rise?
The number of bacteria.
So we have the number of bacteria. So what's the unit of run?
Hours.
Hours. So the slope is, the unit of slope is going to be the number of bacteria divided by hours. So what does this actually mean? It means, and this is a little bit important, like how do you interpret this number? On average, because we're finding the average rate of change between the hours of 0 to 2, yeah? Slope is positive. The bacteria is increasing, our bacterial count is increasing by 136 bacteria per hour. So that would be the interpretation. If the slope is positive, it's increasing. If the slope is negative, it's going to be decreasing. Now we don't have to do all of these, but where do you think the highest slope would be? Between 0 to 2, 2 to 4? But just look at the numbers. It's increasing and increasing. Like the difference here was like 100 between these two numbers. The difference here is going to be like 300, 500, 600, like 900. The difference in the x values is always 2 because we're going in increments of 2 hours. Where do you think the highest slope will be? Between which intervals? 0 to 2, 2 to 4, you have what, 5 options? Yeah.
8 to 10.
8 to 10. It's going to be when the y value difference is the highest, which is going to be between 8 and 10. Okay? So what that means is if you were to draw the secant lines, you're going to start off like this, and it's going to become more and more vertical. The more vertical the line is, the greater the slope. What's the slope of a horizontal line? So you have something like this, y equals 3. What's the slope of this line? It's horizontal. Is it 0?
No.
Yes, it is. The slope of a horizontal line is 0. You can write y equals to 3 as like this. The slope, that is not the right way. If you want to write this in mx plus b form, m is 0, x is whatever, x can be anything. But the b, the y-intercept, will be 3. So the slope of a horizontal line is 0. What about the slope of a vertical line? Let's say you have x equals to 3. What's the slope of this line? Is it still 0? Here, let's do this. I'll show you why it's a 0 for one of them, and maybe it's 0 for the other, or maybe it's not. Let's go back to this example. Y equals to 3. Y-intercept is 3. Let's pick another point here. Let's pick the x value of 1. What's the y value when the x value is 1 for this line?
It's 0.
So when the x value is 1, the y value is still 3, right? When the x value is 2, y value will also be 3 for this line. So when you go to do rise over run for this, what's the rise from 3 to 3?
0.
0. The run from 0 to 1 is 1. So 0 over 1 is 0. That's why the slope of a horizontal line is always going to be 0. You don't have to do rise over run, but that's the idea. Now, if we translate this into a vertical line, let's say we have this x equals to 3, and we'll do the same thing. We're gonna go from the y value of 1 to y value of 0. What's the x value here? The line is x equals 3.
It's 3.
That's 3. What's the x value down here?
It's still 3.
It's still 3. Now, when you go to do rise over run, what's the rise from here to here?
1.
What's the run from here to here?
0.
What's 1 over 0?
It's 0.
1 over 0 is not 0. 1 over 0 is actually undefined. Some say it's infinity, but it's not even infinity. It's undefined. You can't divide by 0. So the slope of a vertical line that's perfectly straight is going to be undefined, whereas the slope for a horizontal line is going to be 0. Okay? That's undefined.
Okay.
You're gonna see this a whole lot, stuff like this later down the road. 1 to the power of 0 is a 1, right? What's 0 to the power of 0? Is it 1? You have nothing, and you're taking it to the power of nothing. Do you get something out of that? It doesn't make sense, this one. It's also undefined. Means we don't know. We do know that it doesn't exist, basically. You can't have nothing and then make something out of it. But this one's a very special case. If you take a function, let's go back to 0 over 0. I'm gonna rewrite this in this form. Y is equals to x to the power of x, okay? When x is 0. Can I do that? And the answer is yes, I can. So now if I go back, we need to sketch this to see like there's something weird happening for this one. Where did it go? What I'm gonna do is I'm gonna go on Desmos here. I'm gonna graph x to the power of x. X to the power of x. Now this is the same idea as our function, right? It's x to the power of x. We're just saying it in terms of 0 to the power of 0. Now look what happens here. Something weird happens. It's actually 1. You see that on the curve? How do you have nothing and you take it to the power of nothing and then get something out of it? How is that possible? It's because what they did was they didn't actually, it's actually not 1. What it is that there is actually a hole there, okay? There is a hole over there. If you do something called the limit when x goes to 0 of x to the power of x, this is 1. It could potentially be 1. But is 0 to the power of 0, 1? No, it's not. The limit is an idea of what the y value could potentially be. but the actual y value is not 1, okay?
Mm-hmm.
Yeah, you can get a lot of like weird things in like math, like 1 over 0 is undefined, 0 to the power of 0 is undefined. What else? 1 to the power of infinity is undefined, 0 to the power of 0 is undefined. So these are like the 4 building blocks of mathematics. Whatever, let's go back to our question here. So over here, we established that the highest slope is going to be between 8 and 10. So here we have a word problem. We are renting a car. She's charged $35 a day and 15 cents per kilometer. They've given us the equation. So the y-intercept is 35. The slope is 15 cents or 0.15. So it's going to be pretty flat. It's not going to be very vertical, but for our sake, let's do it like this. So this is, let's use the notation they did. CFD is 0.15D plus 35. So this is the equation that we have. What's the slope from here to here? Remember, it's a straight line.
It's still 0.15.
0.15. What's the slope from here to here? Does it change?
0.15.
It never changes, right? So it doesn't matter how much she's driving. What's the unit of the slope? Look at the x value and the y values, what they represent. What's the unit of the slope? So on the y-axis, we have CFD, which is the cost, right? It says cost. On the x-axis, we have the daily distance in kilometers. So here it's dollars, here it's kilometers. So what's the unit of the slope? It's going to be rise over run, right? The unit in the rise is what? By rise, I mean the y value. Rise represents the y values. It's dollars. What's the unit in the run?
Kilometers.
Kilometers. So that's the unit of our slope. It's going to be 0.15 dollars per kilometer. So it doesn't matter how many kilometers she drives. It doesn't make sense that we have a negative axis here because kilometers won't be negative. But it doesn't matter how much she drives. The slope will always be 15 cents per kilometer, right?
Mhm.
So for every kilometer she drives, she's spending 15 cents on average. That would be the interpretation. It's completely independent of the x value. Here's a question similar to the first question. Where do you think the slope is the greatest? Between which two values? I'll give you three options. It's initially, it's in the middle, or it's at the end. Where do you think the slope is the greatest? The higher the slope, the more vertical the line will be. Keep that in mind. If you compare this with this versus this is option A, option B, option C. Which one of them has the highest slope? Or which one of them is the most
A.
vertical? A. So the greatest slope will be over here, okay?
Mhm.
We don't even have to do the maths, but if you wanted to, it's because this difference between the first two y values is greater than the difference in any other. Like this is almost like 356, whereas this is only like 200, and then it's going to go down and down and down. Well, or this difference at the end is only 10. So the greater the difference in the y values, the higher the slope will be, okay?
Mhm.
don't have to do part A. Part A is basically just plug and chug, while f of b minus f of a. But here's some concept questions. Look at part B. Why is the rate of change negative? Now, if you looked at our lines, they were all going this way, which means it's negative. It's going down, it's falling.
Mhm.
Why is it falling? What's the logic? And it has to do with the context of the question. You have a tub and it's being drained. So water's gone down into the pipes, well, eventually into the ocean. But what's happening to the y values? Look at what's happening to the y values.
It's going down because the
Yeah.
water's leaving.
Exactly. So the y values are decreasing, and if the y values go down, then the slope will be negative. It's because the tub is being drained. Part C. Does the hot tub drain at a constant rate?
No.
No. This is basically asking, is the slope the same? No, it's not. The slope is the highest initially, and then as the tub has less and less water, the rate of change is going to go down, and eventually it'll become 0 when the y values are the same, or when the y value hits 0. Okay, over here we have a quadratic h of t. We're at a cliff, we're throwing a rock. All right, let's look at this equation. H of t is equals to negative 5t squared plus 10t plus 120. So this is a quadratic function. How do we graph a quadratic function? What do we need? We need 3 things to be able to graph a quadratic. Remember? You need the y-intercept. You need which is already given. You need the x-intercept, and you need the vertex. How do you find the x-intercept of a quadratic? You're gonna factor it, okay? You man it, basically. Trinomial, if you have a trinomial, you're gonna man it. So let's try manning this. So negative 5t squared plus 10t plus 120. If you can pull something out, always pull something out. I'm gonna pull a negative 5 out. So I'll be left with t squared minus 2t minus 24. Let's look at this one. We're looking for 2 numbers. And if the man doesn't work, you would have used the quadratic formula. You're looking for 2 numbers. When you multiply them, it's going to multiply to negative 24. When you add them, it's going to multiply to negative 2. What are the 2 numbers? It's 4 and 6, but one of them is negative. Which one is negative?
6.
Yeah, so it's 4 and negative 6. So you have negative 5 t plus 4 t minus 6. So now we've factored it. To find the x-intercept, you want to set it equal to 0. Divide both sides by negative 5, this disappears. Your first x-intercept is negative 4. Your second x-intercept is 6. So these are your 2 x-intercepts. How do you find the vertex using x-intercepts? Vertex is going to be in the middle, right in the middle. What you do is you first find the h value. which is the midpoint of your two x-intercepts. What's the midpoint of -4 and 6? This is the midpoint formula right here.
It's 1.
It's 1. So that's your x value of the vertex. That's called h. And then you want to find k, which is the y value of the vertex, by plugging 1 back into the equation. So I'm going to plug 1 in here. I get -5 plus 10 plus 120. 130 minus 5, it's 125. So our vertex is at 1 and 125 right there. Our y-intercept is 120, so a little bit below. Our two x-intercepts are -4 and +6. So therefore, our curve is going to look like this. We'll just connect all the dots. Did that make sense?
Mm-hmm.
Now, where do you think the slope is greatest? At the vertex, or on the y-intercept, or on the x-intercepts? I'll draw lines. So at the vertex, the slope will look like this. Over here, it'll look like this. Over here, it'll look like this. Where is the slope the greatest?
Where the x-intercepts are.
Where the x-intercepts are. So for part A, it's just a plug and chug. Here, let me just do one of them at least. So between 0 and 1. So it says between 0 and 1. The formula for average rate of change is f of b. So b is 1. B is always the bigger number of the two, minus f of a over b minus a. So what you want to do is you want to plug 1 into your equation. So I already did that. Did I? Yeah, we did. It's 125. When the x value is 1, the y value is 125. Minus, look at this equation. When the x value is 0, what's the y value? We already have that number here. When the x is 0, what's the y value? In other words, what's the y-intercept?
It's 1.
It's 120. When the x value is 0, when t is 0, -5 times 0 is 0. 10 times t is 0. That's 120. So 125 minus, when the x value is 0, the y value is 120, all over b minus a. 1 minus 0. So the slope is 5. The units on the x-axis is meters. The height, sorry, on the y-axis is height. So it's going to be meters. And the unit in the x-axis is time in seconds. So meters per second. Does the slope being positive between 0 and 1, so which is this line, this secant line here. Does that make sense for the slope to be positive? Is this a positive slope or a negative slope? It's increasing, right? The y values are increasing, so the slope should be positive. Yes, it does make sense. Now, if you found the slope from 1 to 2, which is going to be this secant line here, this secant line, would you expect the slope to be positive or negative?
Negative.
Negative. Why is it negative? Because of this rock or whatever this guy tossed. Yeah, it's a rock. It's falling, right? The y values are decreasing, hence the slope is going to be negative. So by that logic, you can just plug and chug for 1 to all of these 4. The slope will be the greatest over here, between 3 to 4. Towards the x-intercepts, the slope would be the greatest, away from the vertex, because exactly at the vertex, there's a turning point. What do you think the slope is over here? It's perfectly horizontal. The slope of a horizontal line,
It's 0.
it's 0. So the further away you go from the vertex, the bigger the slope will become. And that's the answer to part B. As a time increases, what do you notice about the average rate of change? So over here, it was positive, right? For 0 to 1, it's positive. For 1 to 2, it's going to be negative. 2 to 3, it's going to be negative, but the number is going to be even bigger. And then finally, from 3 to 4, it's going to be even bigger. As you follow this down and down and down, the slope is going to increase and increase and increase. Describe what the average rate of change means in this situation. So we know the units for the slope is meters per second, which is speed. Meters per second is speed. Meters is distance, time is seconds. So what's happening to the slope? We're not actually concerned about the negative quadrants here because time cannot be negative. And also, let's stick right here. In other words, let me just redraw this. This is our curve. This is all we're interested in. What does the average rate of change represent? The answer is in the units. It represents the speed of the rock, right? Speed
Mhm.
of the rock. Meters per second is the unit, which is a speed. And he's throwing the rock. So it's gonna go up. It's gonna hit a vertex because it's a quadratic, always has a vertex, and then comes down and crashes into the water. Is this making sense?
Mhm.
Like over here, even without plugging in the numbers, right? Where would you expect the slope to be the greatest? Between, look at this, 0 to 20 is this. 20 to 40 would be this. 40 to 60 would be this. Where would you expect the greatest slope? Between which two x values?
40 to 60.
Yeah, 40 to 60. And as you go away from the vertex or whatever this is, the starting point, the greater the slope will be, okay? Here, let me just quickly do one or two of these. So for AI, we're going from 0 to 20. So we're going to use f of b minus f of a all over b minus a, which means the y value at 20, which is 20, minus the y value at 0, which is 5, all over 20 minus 0. So that's 15 over 20, that's 0.75. And the unit is 1,000 people, or thousands, per year. And let me just do one more. For III, the third one there, the y value at 40 is 80, minus the y value at 60 is 320. I flipped it. It should be f of b. So first the y value at 60, 320 minus the y value at 40 is 80, divided by 60 minus 40. That's 240 over 20. That's 12, or 12,000. So that's how you do part A. And as you can see, the population growth, this is the rate of change of population over time, or the slope of population over time. It's getting bigger and bigger, right?
Mhm.
Is the population growth constant?
No.
No, it's not. It was pretty low initially, and as time went on, it became more and more and more. Yeah. Part C, to predict what the population will be in 2050, what assumptions must you make? We're gonna assume that this model, right, this appears to be an exponential model, goes on over time, okay?
Mhm.
So that's how we kind of predict, like, like when would hit 9 billion and this and that, like what the population will be like in 2050. You use data points, you make a model, and then you make a prediction. See if that, and then eventually we'll know if we were right or not, but this is what the trend appears to be. This is called an exponential growth model. But the population is growing exponentially. But in real life, the equation for that would be what? N of t is the final population, is equals to N0, the starting population, times E is the natural number, like pi, it's like 2.717 something, to the power of the population growth rate, R, times T. This is the population growth model, exponential growth model. But in real life, it's a little bit different because think about it this way. You have a bacteria, okay? Let's say this
Mhm.
bacteria, whatever it is, E. coli, doesn't matter what it is, a virus. Let's say it doubles every second or every hour, doesn't matter. It doubles like this. So eventually, over the course of a day, you'll have trillions of these, right? And these do exist out in the in real life. So the world should be covered completely with bacteria and viruses. If you follow this model, there's going to be trillions and trillions and trillions everywhere. The question is, why isn't it? Why aren't we covered in E. coli or whatever? Since they reproduce so quickly, so why isn't that happening? It's because these guys need resources to grow, right? Everything, resources, by resources, I mean food and energy, I guess. Food and energy. They're gonna need this to reproduce and grow and grow and grow. Do we have unlimited resources?
No.
No, we don't. It's because of this. They're bottlenecked. Bottleneck just means constrained by the fact that they don't have unlimited amount of resources. So this could apply to humans, I guess, for now. At least it did in the past. But now, what instead of an exponential model, which would grow forever like this, what we now have is something called the logistic model. The equation is pretty nasty, but what it looks like is this. Where this, there's an asymptote basically. There's a horizontal asymptote here. This is called the K value. And this K represents the carrying capacity. There's only so much stuff or so much space and so many resources. Okay?
Mhm.
It could cross this. It has happened. So what happens if you cross that K? What happens if you cross? It's not this is real life. It's not like theoretical maths. So it can definitely cross that asymptote. What happens? There's multiple cases. What could happen, I guess. One of them is that it crosses it and it comes right back down. Okay, like that. And this happens over and over and over again. So this is called a stable limit. It goes up and down and it crosses. Or you could have something like this. It goes all the way up there and then comes down here, and then goes all the way here, comes down here, and like this. You see this?
Mhm.
This is called chaos theory. It has to do with randomness. Or there's many more options. Actually, no, wait, let me think. The last option would be this one. You exceed the carrying capacity so high, right? Look at this. So high that everything dies. This happens out in the wild. We don't see it, but it has happened. It has even happened. I don't know if it's happened to humans, but it definitely happens out in the wild. So this is more realistic, the logistic growth model compared to the exponential growth model. Okay.
Mhm.
So the bacteria that we just talked about, they're constrained. That's why they can't grow forever and ever and ever. What else have they got for us? We can move on from here. So that was the average rate of change. It's the slope of the secant line between two x values. And this is just a straight line. This is just mx plus b. You just find the m value. Another type of rate of change is called the instantaneous. I don't know if I'm spelling this right. I'm going to double check here. The instantaneous rate of change, called IROC. So this thing, instead of looking between two different points, let's go back to our quadratic example. Last time we're finding the slope of the secant line, whereas now there's only one value. There's only one x value of a. Last time we had a and b, now you only have a. What you do is you take that point and you draw a line that's perpendicular to this point, which looks something like this. It's completely perpendicular at 90 degrees. And you find the slope of this line. This line is called the tangent line. So the last one was the secant. This is the tangent. Cool?
Mm-hmm.
So how do you actually find this? It's a little bit more different. So here they've given us another population growth model, which is exponential. It's an exponential function. The growth rate is 1.05. You know what this 1.05 means? For every person that exists today, 1.05 person will exist sometime later. How can we reword that? It's basically you have three growth rates. You can have exactly equal to 1, which is something like Canada. Here, let's go on a tangent here a little bit. You have something called population pyramids.
Mm-hmm.
There's three options. Either there's a lot of kids, okay? This is called the pre-reproductive population. You have a lot of children. Over here, you have the reproductive population. And then finally over here, you have the post-reproductive. These are like the old people. So this is a perfect pyramid, right? Bottom up pyramid, bottom up. This represents a high population growth. You see this? That's our R value, the rate. This represents high population growth. There's a lot more kids than there are adults, yeah?
Mm-hmm.
It's a good example of this. Where's population completely grown? Maybe India, or like China, or like, I don't know, if you go to Africa, maybe Kenya, if you go to the Middle East, Saudi Arabia, something like this. This is a population, very high population growth. But then you have countries like Canada, where the population pyramid looks something like this. So those are the children, right? And then you have a similar amount of reproductive population, and then you have maybe slightly less. It's almost the same, actually. Like it's almost the same. So here this is like R is like almost 1. These people are going to eventually die off, but they will be replaced almost 1-to-1 by the children. Over here, these people are going to die off, but there is more than enough kids to make up for that. That's why the population is going to go up. What's a good example of R is 1? That's Canada. Another one, I'm trying to think. Germany, maybe. These, it's like constant. The population is not growing too hard. And then you have the other ones where it's completely messed up. You have a lot more adults, okay? Then you have the working class or the reproductive population. Then you have the kids. This is the worst case scenario because there is not enough children left to compensate for these people. This is called negative growth, okay? negative growth rate. Can you give me an example of any country where this is happening? One of them is a very popular example. Which country do you think is experiencing negative population growth? The answer is Japan.
Mhm.
They have a lot more elderly people than they have kids, which means they don't have enough population to sustain themselves. Okay? These will never make up for this fact. They will never make up for this. So this is a negative growth rate. This one's not good because these people depend on the economy, but there's not enough people to support that economy. So at this rate, this is gonna be the boom and bust kind of thing that we saw before. So this is a logistic growth model. There's a carrying capacity. They would have exceeded the carrying capacity so hard that it's gonna completely crash. So this is where they're headed. That's why Japan is trying to like ease up on their immigration laws, try to get more people into the country. Another example I think is South Korea as well. This is happening mostly in Asian countries, but eventually could happen to the equals to one population, such as Canada or Germany or something like that. So this
Well, we
1.05,
get a lot of immigrants, right? So.
yeah, it's not happened yet. That's why it's about one right now, but eventually it could happen because not a lot of people want to have children these days because it's not affordable. That's one of the key reasons because the cost of living is so high. So this 1.05 is the average number of people for every person that exists today. So what is the question actually asking us? So this is from 2000 and they want the instantaneous rate of change in 2015. So notice they've only given us one X value here. The T here represents the number of years from 2000. So T is going to be 15. So we only have one X value. Last time we had two. So how do we actually find the growth rate here? The sketch of this looks something like this. We don't care about the negative x-axis because it's time. Also negative y-axis is the number of people, so we don't care about that at all. So it's gonna start at 35,000 and it's gonna go like this. This is an exponential growth model. At t equals to 15, what the question's asking us is to find the slope of this tangent line. That's all the question's asking us. So how do you actually find this? So there's multiple ways to do this instantaneous rate change. There's the perfect way, which I'll show you in a bit, but there's multiple ways to do this. What we do with IROC problems is that we convert them into AROC problems. What does that even mean? You have three possibilities. You want t equals to 15. What we do is we go from 14 to 15, where 14 is your A value and 15 is your B value. So it becomes an AROC from 14 to 15. So over here, one of the possible answers could be f of 15 minus f of 14 divided by 15 minus 14. So let me plug these numbers. So 35,000 times 1.05 to the 15 minus 35,000 times 1.05 to the 14 divided by 1. So one possible answer is 3464. So on average, at 15 years or in 2015, the population is growing by 3464.88 people per year. This would be one of the answers. This is called the preceding interval, where you take a number slightly before your point of interest. So if we're looking at 15, we take 14. The other option, instead of looking at it before, you look at it after. This is called the following interval. So here, last time we had 14 and 15, but now we're going to have 16 and 15. You go one up. Last time we went one down. Now we go one up. So let me plug this in. Times 1.052, and we'll see the pattern here. Times 1.05 to the 15. So this one gives me 3638. So over here, it's a little bit higher, yeah? And well, that's kind of expected because the secant line over here compared to over here, this one will be more steeper. And then what you do is you take the average of these two, and that'll be your final answer. So here, the one good answer is you take the average. You take the preceding, you take the following, and you take the average of them. Plus 3464.88 divided by 2. So one good answer is, so far this is the best answer. You take the before, after, and you take the average of them. So that's one way to find the IROC. You change it into an AROC. Another way is, instead of doing preceding and following, you just straight up do centered. And let's see what this gives us. Centered means you go one down and one up. So here we will go from 14 to 16. 15 is right in the middle. So we'll go from 14 to 16. Here I'm going to cheat a little bit because we're running out of time. But so this one gives me 3550, right? If you use the center. So which one's the best? Do you take the average between preceding and following, or do you take the centered? So the answer is you take the centered. This one is the best. You go one down and one up. But all of these are just approximations. There is one true answer, which I'm going to leave it as a suspense for tomorrow. So let's call it a day there.
Okay, thank you.
So yeah.